Welcome to Flat Earth Debates Special Edition. I am rejoined by Chris Monk and Anthony Riley after presenting a flat Earth model of the Isle of Man. So we're going to have a bit of a chit chat and hopefully interact a little bit with the chat. So let's just reintroduce Anthony and Chris. How are you gentlemen doing?
Doing good. This is the best part for me because I can interact a little bit more and just see where the conversation goes.
Cool, good stuff. I'm going to minimise the Skype page for now, just so we've got a bit more of a nicer backdrop with a bit of a sunset. But if you do want to present something, just tell me and I'll pop it back open. But yeah, so I'm over the moon. We've just presented, or Chris has just presented to be more accurate, the flat Earth model, which has been massively hyped by me. But I'm just chuffed that we've actually got to show it for the first time. How did you feel it went, Chris? Are you pleased with the way it was presented?
Absolutely, yeah. No, I was pleased, and I was always a little nervous when you're trying to present technical stuff and sound, like you're trying to explain things in simple terms.
Can I
came across okay? Right?
Can I just say to everybody in chat, I was actively muted, gagged, and controlled by Nathan. I wasn't allowed to speak in that last one because all I wanted to ask was, "Where's the curve?" And he wouldn't let me do it. So now this is the show where I can say, "Come on then, where's all that lovely curvature that's supposed to be there?" And obviously the answer, of course, is there is no curvature. The Earth is flat. And basically the biggest problem that we had when we were trying to agree on this scale, not so much the scale, but what we were looking at, the floaty land in the north, it was so difficult to get consensus on it because it doesn't match at all with the curve, the spherical nature of the Earth. So you've got like Rumpus and GeoStreamer claiming things like, "Oh, well, it matches the sphericity of the Earth," and it doesn't at all. There is no reason whatsoever for that land to be there on a ball, unless the ball is a lot smaller than what a lot bigger than what they tell us. And I'm happy that it's not anymore. The Earth is flat, but I couldn't get my head around why it was so prominent. That land was, I mean, we're seeing that land. It's above 100 feet because we know that Ramsey is hidden behind that refraction layer, that dirtier or whatever you want to call it. That whole town is behind that, and that's 100 feet. So whatever we're seeing is above 100 feet tall, and there's only one explanation for it, that it's flat. But we were trying to apply it to the curve calcs, and it was nowhere near. So all these idiots on the ball side, like in that Steve hangout that we had the other day, that never even happened, we didn't even get to this point. But there was no curve. And I was dying to look. I was looking forward to how they were going to explain why the land is there, and we didn't get to that point at all because Rumpus was just literally waffling about nonsense. And in the end, it got to the point where, without even addressing the land, Steve declared that the observation was invalid, without even explaining why. So this went on for weeks and weeks and weeks. Why is there so much land? And the only explanation is because the Earth's flat. But when you're trying to make it into a ball, you're trying to put the bit of curve in it, and there's no curve there. The only explanation is it's flat. There is no other explanation, and we didn't even get to that point with Steve. So I was gutted, but it's been a battle for me because I've been trying to play both sides of the coin. So's Ranty, and we've not always agreed. It's been hard. There were times when we vehemently didn't agree with each other because we were trying to put curve into it to see how much curve there should be and all, and there is none. It's flat as a pancake. Flat.
I mean, we've added Ranty to this call. I hope he does join. He's busy at the moment, but it's just one of those things. I was hoping he was going to go through some of the experiences, shall we call them, that he had with Google Earth, because he was tearing his hair out. It was so frustrating going back and forth and back and forth and back and forth. And even on the debates, people who have seen us going back and forth on those Google renderings. And it's a nightmare. It's so easy to misidentify reality with that software. And that's what we've got to use. That's the tools. It takes a huge amount of work. I mean, how many hours do you reckon have gone into that model, Chris?
Into the Google model, you mean?
Nah, into the model that you made.
Oh, right. Well, the first one where I went through and modeled the spherical globe model and then had it fail. I mean, that probably took, a week or so, probably 40 to 80 man hours for sure. And then the second one, not as much because it's a lot simpler model, but the testing of it to make sure things were working okay and stuff. And, it's another 3-4 days solid work, and then research and the research to back it up as far as having to research distances and elevations and, lighthouses and everything else, right? You got to look up all the data. And 3-4 weeks of pretty solid part-time work. 3-4 weeks.
Yeah, you were doing the whole time we were debating about it. Basically, every single day that the debate was going on, you were modelling it and testing it, modelling it and testing it and remodelling it and starting from scratch, recompositing, starting from scratch. Yeah. I mean, I know exactly how long I was watching you do it, but it's nice to hear you made it sound like it was actually, it's just a week's work. But on the contrary, I think you put in a lot more hours than you're letting on.
Yeah, I didn't track it. Maybe I should have tracked it. But even, listening to the debates and, even taking the opposing sides, their ideas and whatnot, and then putting them to the test in the model to see if what they're saying is factual or how their approach is, or because I'm interested in understanding how it is that some relatively complex mathematics, like some of the math that Rumpus is doing and those other guys, that's complex stuff, right? And how they're trying to apply that to a spherical type of reality in their minds to justify. You don't see curvature on the horizon and this and that and everything else. Like everything is apparent in a flat reality, and yet somehow through mathematics, attempting to justify, it's kind of reverse psychology, right? It's like we don't see it and you can't see it because it's too big, etc. So we justify it with this complex mathematics.
I mean,
I don't know. It's a very interesting psychological effect. It's like self-delusion, right? You're actually mathematically proving to yourself what your eyes don't see.
Yeah, I just want to rudely interrupt a sec. Nate, do us a favor, show me screen.
Okay.
I just want to give a shout out to all those idiots on the Ball Earth side that were arguing. Why haven't you gone to the press? Why haven't you told everybody? Well, I'm pleased to report that finally somebody's picked up on this, and it's 3FM, which is the Manx radio, I believe. They've picked up on it and they've documented and reported on it. But sadly, they've done the one that we'd released the other day from Landudno. But nonetheless, it doesn't make that much difference. The point is that we are now officially recognised, published, and promoted by a national media coverage, which can only be a good thing. So that adds to the credibility, boys and girls. So hopefully that should open some more doors, and it should create a little bit of interest. And now, if we get a little bit of interest out of this can only be a good thing. So shout out to Jason Roberts, Chips Gravy, or whatever his tweet thing is. We'll be getting in touch with you soon. But that just adds a little bit of credibility to all those idiots claiming, well, why haven't you gone to the media? Well, finally, it's beginning to work. So, nah.
I mean, I was hoping. I mean, I'm chuffed about that. I won't lie. Manx Radio. Thank you very much. What was the guy's name again?
Chips Gravy. Jason Roberts.
Thank you very much, Jason Roberts. Really, really appreciate that. But I was hoping that Chris would explain something that was obfuscated, talked over. You were belittled during this, but basically, the Rumpus did an arc calculation on the vertical axis when he was asked to give a angle measurement, and I want you to talk through exactly what that means and the implications thereof, and then hopefully at the end do exactly that in your model in about 15 seconds flat. But can you talk us through what happened on Steve's debate when we abandoned you like complete cowards?
Speak for yourself.
Yeah. Well, maybe Anthony, you got a couple of screen grabs there from that particular hangout there that show when Rumpus held the ruler up to the. Essentially, yeah. I had asked if Rumpus could calculate essentially on the fly what the angular elevation of Snaefell Mountain would have been, because I knew it was at 2,013 feet of elevation in physical reality, and if he had done the math, it would come out to be around 0.5 degrees plus or minus a couple of decimal points. So if you could pull up the picture maybe and share it on the screen, I could.
Am I not sharing?
I don't see it.
No, not at the moment.
Hang on.
It's all right. We don't have to be slick on this. We're not. This is the after show and we chit chat. Doesn't matter if it's slick.
That's okay.
We can mention people. Like, don't mention anybody's names. Right.
Yeah, there's a couple of pictures. Yeah.
Right. So that was the first answer he gave with regards to the question. Just re-ask the question.
Well, the question I was trying to get across was, what is the angular elevation in degrees, angular elevation to the top of Snaefell Mountain, which is actually up in the clouds there, but it would be at 2,013 feet. And the first calculation he came back with was 0.41 degrees, and then it got altered to 0.5 whatever degrees.
Well, the reason, I'll just give the reason he gave, though, just so I do have his Weasley excuse. So after spending approximately, I'm going to give him probably less time than he actually spent, but an hour arguing that Anthony was higher in elevation, when he came to calculate this, for some reason, he calculated it at the lower quoted Google elevation that they've all consistently said was incorrect. So he calculated it at 35 feet. I don't know why. I picked up on it and thought, why has he done that? And then when he got it wrong, that's what he blamed.
Right. Yeah, I see what you mean. Yeah. So yeah, if you leave that picture up for a second there, I can I was trying to get him to go somewhere, right? And it never happened because it was, like I said, I was talked over and he never got to the end and I couldn't really get an answer to the question. But even at the 0.5 degrees, then you'll see that his first instinct is to put 0 at the horizon line, which means that is a straight line of sight in a flat plane across the water, 31 miles to the Isle of Man. Now, if you were going to do it according to the ball mathematics, the 0 would actually be below sea level to account for the so-called 170 feet of bulge. Right, so you'd actually have to drop that all down another half, whatever in gradients of degrees, if you're actually physically applying ball mathematics. Right, so there's essentially what Rumpus did here was prove the flat plane works, essentially, because when I do it in the flat plane model and take the camera at that angle and tilt it up to the top of the mountain, I come up to, like I did in the demonstration there, 0.537 degrees, I think it is, to 2,013 feet of elevation.
Can you just do it, Chris?
So the second, yeah, I can show you.
You have to share your screen.
So just so there's a side by side. So while you're doing that, what Rumpus did in terms of his working out where things are as you traverse the image from left to right or from right to left is take an angle calculation and then draw a straight line based on what he'd calculated per pixel. So, in other words, when he's assessing this picture from left to right, he can just draw a straight line to whatever he's looking at. But when Chris challenged him to give him an elevation based on a per pixel measurement, instead of doing it with just a straight line, he took about 20 minutes approximately. That might be over exaggerated, it might be pessimistic, but either way, he took quite a considerable time to go and get an arc calculation for the vertical. And correct me if I'm wrong, but that was actually fed to him by Soundly in the side chat after a lot of obfuscation. Is that right, Chris?
Yeah, there was a lot of sidebar stuff going on. There was, calculations, being traded back and forth. They kind of disappeared. And then I was essentially, character assassinated or whatever in that hangout, or at least attempted to be doxxed and all kinds of stuff while they took the time to do these complex mathematics to come back with something that matched the ball math. Right? It was an interesting.
Can you address why the horizon has been set to 0 from the scale that Rumpus used? Why did he do that?
I don't know. I'm not sure whether that would be cognitive dissonance.
No, what? Hold on. No. Didn't he say that the arc calculation was taken from the horizon, which would be the top of the bulge? You asked him for an angle from the observer at St. Bees, from the camera, and what he came back with was an arc calculation from the horizon.
Yeah, which doesn't really, it makes no sense, right? When you think about it, right? The angle of elevation is always relative to the observer at your point of elevation, angled up to whatever it is you're looking at through a straight line of sight, right? So the horizon is, is not. I don't know how he's trying to pull that off. Doesn't make any sense to my mind. But
Well, he
it's
didn't
not
because
applicable.
you cornered him. So afterwards, you said, bring up your picture of your million layers of glass going through the atmosphere, causing a million Snell effects. And when you asked him to say, well, where's the angle? He obviously can't do it.
That's right. Yeah.
So really,
Well, that was the reason I was trying to get at it, right? Because the calculations they were doing were, from left to right, calculating angles per pixels going left to right to determine, distances across the other man through essentially a cross-section view, which is actually orthographic, which it makes no sense either because you're not swinging an arc in an orthographic view. You're now using square, flat plane type of math. But so that's kind of contradictory because applying pixels per degree through a flat plane image is not exactly pixels per degree because degrees are based on arcs, right? However, the premise I was trying to go for was that, okay, if you're doing it from a left to right to measure distances, say from Lang Ness or whatever you're trying to investigate to the Winky Lighthouse or the overall distance across the entire island, that same math should be applicable to the vertical. Right, so I was trying to say, show me that in the vertical that your arc pixels per degree per arc can actually predict the elevation of 2013 feet. And obviously it failed because, the first one came out low, the second one came out low because that is still not where the top of that mountain is. It doesn't work. And
So what's he proving by not getting the maths to apply to real world?
That it's flat. Right? It's a whole lot simpler to do it using straight up Pythagorean elevation 2013 feet, distance of 31 miles. Take the angle of 0.57 degrees, which is the pitch of the camera through a straight line of sight, equals exactly 2013 feet. It's flat mathematics.
or to put it
There's
another
no
way,
arcs.
you draw straight lines to things because that's how we see, and it works out. If you draw curved lines and calculate for curvature, it doesn't match reality. The picture won't match. In other words,
Right.
it's flat.
Yeah.
Right. I'll try to share the screen here and I'll show you maybe another quick little demo of what I'm getting at here.
Shout out to John Watson in chat.
Yeah, so you can see in that picture where the 0.5 is, it's still below the elevation of Snaefell because Snaefell is actually higher than the mountain that's in front of you, right? In reality, but I'll share I'll share it in the model here, and you can see it. Okay, so in the bottom, let's zoom out here a little bit. So again, the target is where the observer is. The camera is the one that's highlighted. And I'll zoom in so that the camera is now looking across the plane to the top of Snaefell Mountain, which is appearing in the image at the top here. I'll rotate the camera around to try to hit that target and then grab the camera. Let's see, rotate. Why did I want? Yep. And then bring the camera up until that line touches the top of the mountain on the bottom. Right. So now I can get it right to an inch if you want to, like right to the top. Rotate Y. So now I measured the angle from the observer to the top of this mountain at 0.569 degrees. And you take the distance to this distance here and calculate it back. You plug it into a trigonometry calculator, and 10 seconds later you've got 38.22 miles. And that's actual proper elevation relative to your observation point. Right? It should have took 10 seconds to figure that out.
Yeah.
It took about 20 minutes. Correct me if I'm wrong. If you're doing it based on living on a sphere, if you're doing the maths, should the distances not increase as things curve around and away from you? Not much, but subtly. Should they not increase?
Well, they would because it's an arc, right?
Yeah.
It'd be
It's
an
not,
arc.
it's not subtly, it's exponentially.
right?
But at this distance, when we, or I keep saying we, I've got to give you more credit, Chris. When Chris overlaid the Google Earth map with the LiDAR map, you could see that at this distance it is subtle, very subtle. So therefore, if that's applied to, the curve that should be blocking your view, the same principle would apply to how much it tilts over as it goes backwards, and how much that increases the distance from your perspective.
Yeah, exactly. Let me show you here.
But it would be subtle at this distance. You wouldn't see much difference, but there would be a difference.
This probably could show you kind of
Here
what
we
we're
go.
getting at. Yeah, so this is basically the calculations that are being applied on a website that I won't mention because it's not mine, but this is a diagram from a website that you can find online. Feel free to look for it. And this is what they're trying to say, is that you're an observer, and in reality, we all know that when you look out, you're looking out through a straight line of sight. So a straight line, surface level, they've got it as a straight line, eye level is a straight line, so far so good. However, doesn't really represent surface level. This is referencing the surface level where the observer is back here at this point. The surface level of a ball would actually be this curved line, right? The curved surface of a physical ball. Then they say, well, in order to see the horizon, you physically have to be looking down. So the higher you go, the further down you have to look. And that's again why I was looking for that angle of elevation from the point of the observer up to the mountain height is a straight line Pythagorean triangle, right? 2013 feet, half a degree. You calculate it on a straight line of sight. That's what you get. So what we're seeing is what we're getting. As simple as that. But you don't have to apply any crazy arctangents, cosines of that, and everything else to get what you need. It's really simple. Because if you believe in the ball reality, this is what you have to believe is actually happening. Right? You're looking over the curve of the surface.
And of course,
hump.
There is no. I was going to say there's no hump.
Well, yeah, there would be in physical reality. Like if you're this camera looking out tangent to a curved ball, right? You're looking out, and you have to maintain your level to the center of so-called gravity of this so-called ball, and you maintain a level line always, straight down, straight out, right? Relative to that so-called gravity, but this isn't reality.
Yeah, they're engineering in something that doesn't exist in your field of view ever.
Ever, yeah, right. Because if you, according to this diagram, when you superimpose it on a physical 3D ball, even if I go into, it might be even easier to see in solid mode. Well, no, I guess you'll lose the background, so material. All right, so you go into this view here, and if I remove the ball, right, what they're trying to sell you, and I'm going to say sell because that's you got to be sold basically down the river with this one, is that you are physically trying to look through this bulge of 170 feet of water if you're going to see from this point over here at your observation point to a target that's supposedly hidden behind the curve is being hidden by a bulge that you're looking down through. You'd physically have to be looking down through a 170-foot mass of water. If you turn the ball back on physically to see that object over here on the surface, not this surface of the ball, you have to physically look through that water to see it. However, in order for that to appear to you in reality, not reality, but actually, if you believe this is what has to happen. This object has to rise up to your eye level magically using whatever kind of mathematics and excuses you want and appear to you on this line of sight, right back up this distance of supposed drop and hidden. It has to rise up to here to be seen by your eye, whilst also, like this object, if I put it to this object here,
While you
do
that, Chris, can I just reiterate what you've just said? So you use the term rise up, correct? That was your terminology?
Right.
Right, so
Yeah.
this is for all the people like Dawn Treader and Cat Earth and the people who simply don't get it. Right. There is
Imric.
Imric, yeah, there's a whole list. Let's not shame too many of them. They all know who they are. The people who ask where the beach is, blah blah blah. Right. Bottom line, this stuff cannot be seen. It is hidden. There is a wall in the way, and when Chris uses the term rises up, that can equally be substituted by a disingenuous baller with the word looming. Or it can be made a farce of by someone like me by using the word hologram. But ultimately speaking, the effect is the same, something that physically cannot be seen because there is a hill or wall, whatever your preference, in the way. It has to be, as Chris termed, risen up or elevated, projected up, whatever you want to describe, but it has to be physically raised from where it is in reality to being able to see it in your vision. So it's not physically there, it's an optical effect that gets termed as slightly looming, non-standard refraction. That's what we're talking about when Chris gives that. It's that term. It has to rise up.
That's exactly it. Yeah.
Nathan,
This is what I'm trying to illustrate here is that if you're on the top of the ball looking out on a flat, straight horizon, right, you're maintaining a level line of sight like you would with a transit or a level or a camera or anything else. This object that I got highlighted over here where it says drop and hidden is physically below this, the top of the ball. Like you actually physically have to look through it to see this object at all. And not only that is when this object rises up to you, if you take a picture of it, whether it's a building or a mountain or anything else, lighthouse, doesn't matter, anything, for you to see it, rise up to this horizon line on the left-hand side here where the wire frame is. I'm going to bring this object up so you can see it actually appear to you in the camera, because this is a camera view. This is the model view. You got to grab it and raise it on the Z until it comes up into your view, level to the horizon. And then, because now it's tilted backwards on the ball, I also have to take it and rotate it on an axis to bring it back into, basically on the X. Let's see. Basically, I have to rotate it to bring it back into 90 degrees, roughly, right? So the object has to stop leaning backwards, magically rise up to the horizon, tilt itself forward to appear to you in a photograph as a straight object. That's some pretty fancy magic, right?
Yeah, you've got to do some pretty crazy mental acrobatics to actually believe that's occurring when you just take a picture of something and stuff is just in the picture. I mean, you phrased it, I can't remember if it was on the globe debunking QED, but you said in the globe world, nothing is where you think it is. And no war would ever have been fought, no bullets would have ever killed anybody, because everything that you're pointing at wouldn't really be there if there was a million layers of glass in our atmosphere refracting everything on an arc tangent. It's ridiculous. Everything is where you think it is. That's just a nonsense that you have to believe if you want to live on a spinning ball flying through space.
Exactly. That is precisely what you need to believe. And I don't know how it is believed, but I don't know. I have no explanation for that part. But you can demonstrate it to be false. I mean, it's completely falsifiable. Right? There's another way to look at it. Another way to think about it is if I bring this object, which is actually quite large in this model, it's like miles high, 1.8 miles high, and right, it's huge. And bring it to you as an observer on the top of the ball. So I brought it up closer to your perspective, right? So now you can see it's in the camera here on the side. You're just seeing the bottom of it. So this would be like standing in front of the CN Tower or the Eiffel Tower or something at the foot of a giant skyscraper, right? And if I take this from your perspective and rotate it on the x-axis relative to the ball here, let's see, relative to the cursor, grab this object, rotate it on the x-axis. So now it's going away from you on the horizon, falling back on the curved surface of the ball until you can just barely see it. So this would be like simulating what it would be like to stand looking, back at the CN Tower from miles away. Right, as the object falls away from you across the curve, it starts to tilt back because by default, it has to maintain a straight line to the center of gravity because gravity is what the entire globe model is based on. There's no choice but to maintain that aspect of an angle to gravity relative to you. So you start to swing an arc, this must tilt backwards and fall away from you, right? Which is why if you bring it back into a straight line of sight, you have to bring it up to the surface, tilt it forward, bring it back into straight lines. And once you start to get your head around that, to me, it's just completely ludicrous what what's being told to you. Right? It has to. There's no other way to do that. And then this is a bit of reverse psychology because the angle here, this angle, tilt, right, is representing what buildings would be. Right? Buildings on a ball would be tilting backwards. So that, show me any measurement anywhere where you can go from, like, I guess in England would it be what, Big Ben to another big building somewhere across the entire city of London, and show me where the bases of those two buildings are closer together and the tops of those two high buildings are further apart, because that's physically what you would need to measure. The distance between the bottom here on this curved surface where it says height and hidden, so you take those as 2 points that are close together, and it's like you were saying earlier, the arch, the higher you go, the arch gets longer, right? So this, from your eye level to the top of the building over here where it says eye, to the top of a building over here where it says tilt, would physically be further apart than the bottoms. The bottoms are closer. I mean, it's an angle, right? Does that make sense?
Yeah, it makes perfect sense. I mean, you summed this up beautifully just before we went live while we were prepping for this after show, when you said that if you look at how a cityscape is actually laid out in blocks, you can see that the things at the far end of the city aren't tilting away from you. You don't have skyscrapers that get wider towards the top to account for this gravity nonsense. It just never happens.
No, it doesn't. No. I mean, if that was the case, you'd have, like, say if you had a major building in the center of a city as your main point of your reference frame, like this is your reference point. Every building in the entire city would be falling away from that particular building in all directions in 360 degrees, all tilted backwards away from that center point, no matter where you are, right? And that's just not our reality. It's like, it would be like a chia pet. Like if you took this ball and put hair on it, right? It's like a chia pet, just hair spikes growing out of it everywhere. Right? You can actually turn a few of them on. Right? And I'll just hide this plane. Right? Right? If you look at these in a physical sense, I mean, that's what would be happening on a ball. If you highlight every one of these, right? Right, as they go backwards, right? Not only to maintain visibility, like they would physically have to grow higher and higher and higher and higher and higher in order for you to maintain visibility if you're looking out at them.
Right. We've got people like Miles Davis going out and capturing wind farms and claiming that the curvature just seems to creep from the bottom up, but doesn't cause any of these effects of leaning over the curve that apparently is obscuring them. It's a nonsense. I mean, Sly Sparkane has been in this morning's chat saying, you guys need to get on the beach. You need to anchor your tripods in the water, and that's where you need to be taking your observations from. And until now, Anthony describes something that you called the circle of confusion as dirty air. Can you bring up? Is there any chance you can bring up the Isle of Man model and just show us show the audience what I'm talking about?
And not just show the definition in terms of science, because it is actually a scientific phrase. It's not a phrase that we've made up.
Circle of confusion.
Yeah.
Yeah, if you want to Google that, if you want to look it up there, circle of confusion photography, I'll just close out with this little demonstration here to finish my train of thought on this model. Here was the, well, we were talking about the curvature and how these buildings would have to tilt away from you and whatnot, right? And the reason that what they're doing is trying to compensate by saying that the camera is tilted down. right? So they're saying, okay, the camera's tilted down, looking at the horizon, and that's where it supposedly intersects to accommodate for so-called curvature and the bulge, right? So the camera point of sight cuts through to the bulge and ends up at the bottom of this building that I had earlier highlighted, right? So it's now meeting this point here. This is our camera. It's cutting through the ball to meet the bottom of this building. But what doesn't happen in reality is if you grab that camera and start to raise it up as if you're in a rocket or an aircraft or anything else, like going up an elevator in a high building, you can see on the left-hand side, it looks relatively level at this point. And as I raise the camera up, watch how quickly the curvature appears to you as an observer. Right? So if you're on a ball and you're raising up, in reality, that's what you would physically see. Like you should see, the higher you go, the more curve you should see, because you're raising up and looking over the surface of a ball. Right? Just want to kind of drive that home to people, right?
Yeah.
If you're down on the ground, sure, it might look flat because you're on a big ball. But as you rise, there should be ever more exponentially visible curvature.
What the calculator that you say... Sorry, Chris, to interrupt you. I just wanted to add this bit in. So what the calculator shows is the camera tilting down. And what that means, if you're actually doing that, you're seeing more curvature. That's why you're having to tilt your camera down. But it's never ever seen. No one ever tilts their camera down. No one has transits that point down. But ultimately speaking, that's what's necessitated. If you're pointing your camera down, it's because you're raising up on a ball. And as you rise in altitude on a ball, you see it get more curvy until eventually you see a whole sphere below you. But we only ever see one or the other. You rise up and they say you don't see any curve at 30,000 feet, even though you absolutely would on a ball that's 24,900 miles in circumference. You would definitely see more and more curvature as you went up to cruising altitude in a commercial liner. You wouldn't have to be on something the size of... You'd have to be on something the size of Jupiter to not see it.
Exactly right. And this model will test that, right? To prove exactly what you're saying is that because this ball is to the dimensions of the Earth in the globe model. And if you raise the camera up, you can see that, essentially what would happen is if you get up high enough to a point equal to the radius of the ball, then eventually you would see the entire ball appear within your frame of view, right? And never seen it, right? It doesn't happen. You're exactly right. The higher you go, the more curve you should see.
Yep, and yet we have
until eventually you see the whole ball, right? If you go high enough, right, grab his head, and, eventually you would see the whole ball at whatever altitude. But if you imagine you're in a rocket blasting off the surface, I mean that's what it should really look like, right? The balls drop away from you like that, and the camera would be. Right, the higher you go, if you're at an angle, it would just appear as a curved surface on your horizon. The higher you go, until eventually, if you get right down on the surface, then it would start to appear more flat, but still not perfect. Right, there should always be, in every photograph ever taken of a fairly long panoramic view, like if you had a picture of, say, Hawaii from, the coast, I don't know, whatever, offshore, whatever, right? A very long panoramic view of, say, 10, 20 miles, and from your left to your right in your picture is 10 to 20 miles, like the Isle of Man photographs and stuff. If you have a wide panoramic view, you should see this curvature, right? Because
How high are you on this very moment? Epistemology for Truth says he's at least 42 miles. How high are you?
Where right now in this picture?
Yeah.
40 miles high. So,
So take us to cruising altitude.
What's that going to be in
30,000 feet, something like
that? Yeah, 8 miles. Let's try it here. 40,000 feet, 5 8's 40, so 8 miles high. The 8 Mile Club. Oops. Go up to 8 miles. Try and bring it down slowly here. 8 miles. Right. So there's 8 miles.
Yeah, there's no
8
escaping the
miles
ball.
high.
There's no escaping the balliness
Right.
of the ball.
There's no escaping what?
So this would simulate, essentially, yeah, if you were in an aircraft at 8 miles high and trying to keep the nose up at the, towards the horizon, and you were looking out through the nose of an aircraft, and that's what you should see, right? This curvature at 8 miles.
There's no escaping what,
Simple as
Nate?
that.
The balliness of the ball.
Oh, the balliness. Yeah, you're right. I mean, it's when Google Earth, if you pan out, if you zoom outwards on Google Earth to 30,000 feet, and then pan up to the horizon, you see curve with the naked eye that should not be there.
That is not there. Not that should not be there. That is not there.
Should not be there if the Earth's flat, and is there if the Earth's a ball. And obviously, flying around on a plane, we see that curvature if the Earth is a ball. But obviously, in real world, there is no curvature. There is no bend. There is no axial left to rightness. And
Yeah, I mean, this is what it'd be like. So here, this is interesting. We're just chatting about this, right? So this would be a good simulation. So you're at the 8 mile elevation of an aircraft, flying towards, like, say, New York, or coming in for a landing. You're flying over the surface of a ball. Buildings and mountains and all the topology should come toward you, and gradually it would look like that, right? It would be a very strange experience, right? As you went over the surface of a ball, because you'd have to maintain level, right? Because you're always looking like that, right? And you don't see that, right? It's just, where is it? Where does it happen? Right? Very strange.
so, what's your elevation off the surface of the Earth now?
8 miles.
8
No.
miles. Yeah, I said it 8 miles to be
I mean, from the camera that we're looking through now, the lens that we're looking through now.
8 miles.
No, on the right hand view now, where you got the full circle. How far away from the Earth are we there to see that view?
Oh, I don't know. I'd have
Oh.
to.
I mean, we did this
Technically,
exercise a couple of days ago.
Yeah, I did that. I did that a little bit earlier. Yeah, if you take it and put the camera down to 0, right? We can experiment with it. Down to 0. Grab it on the Z, take it up until you see the ball in the frame. You have to be pretty much equal to the diameter of the object, right?
No, depends on the lens you
Close
use.
to it.
So if you were to
Yeah,
use,
well, yeah, I guess you're right. Yeah, it would depend on the lens. If you had a perfect lens, it was a perfect square, aspect ratio to see the entire ball in this picture over here, you'd have to be the diameter of the ball you're looking at to see it, like all of it, which is 7,900 miles. It's basic. It's pretty basic. Yeah. It's like you're looking through a cone, right? So the cone of your lens would have to be, which depends on the actual cone of your lens, the depth of field and the focal length, right?
But from memory,
So, but with the human eye, with a 50 millimeter lens, it'd be pretty well equal.
But yeah, and I think you've got it to about the height of Hubble with an iPhone from memory. The quoted height of Hubble, I should say.
That's correct. Yeah. If I set this to, for example, under camera presets, and we pick up to the top here, iPhone 4S, yeah, iPhone 5, there. So an iPhone 5 would be a fairly decent representation. Yeah. iPhone 5, 8,000 miles high, I should see the entire globe.
No, I've got it wrong
If it's
then.
real.
Sure, maybe it was a GoPro. I'm sure it was a fisheye lens then that was much closer to the Hubble elevation.
Could have been, yeah.
That got the whole ball. I remember the exercise. It was a few days ago.
Oh,
we were just trying to work out how
if you use
low.
a fisheye, I mean, that's how they're pulling that stuff off, right? They're, whatever altitude they're at, they're using a fisheye lens to make the entire thing. That's an illusion, right? Fisheyes are illusion.
Sure, but I was just intrigued to know how low do you need to be, or how high do you need to be?
Yeah.
Or what's the minimum height you could get the whole ball? And I think it was like I think we worked it out to about the height of Hubble.
Yeah, I think it was with the fisheye type of.
I don't even know what that height is off the top of my head, but
I
whatever
can't
height
remember
that
how I
is.
did it now, but yeah, you're right. I remember doing that. It was like it was a fisheye panoramic view, I think. Fisheye. Maybe I had to render it to make it do it. But yeah, yeah. This will simulate that type of stuff, so I would have to take some time to set the fields of view and whatnot. But basically, yeah. See, this is now the camera's very close. Right? It's like I'll bring the camera down to on the Z, and you could be right above it with a fisheye lens, right? Very close, 7 miles. Right? So about the height of an aircraft, right? 7 to 8 miles. With a fisheye equidistant lens, you should be able to get the entire thing in a fisheye type of camera, right? Of course, it wouldn't show you the whole thing; it would just make it look like it's the whole thing. You'd only get like part of whatever it is you're looking at.
Sure.
I'll stop rendering because when I do that, the camera or the fan kicks in, and I sound terrible. But
yeah, glad
that is true, though.
Glad that didn't happen during the presentation. So just timed it perfectly. So as soon as the presentation ended, all your fans kicked in, and perfect timing. We could hear you nice and clearly in the presentation. You've been very quiet, Anthony. I was expecting you to be tearing into various ballers who have led people astray along this merry path.
Well, I was waiting until we get back onto the composite. If we can we go back to the composite and the overlay and the model itself? Because what I really want you to address is the. Do you remember the 3 or 4 dots that were on the far left of the picture? Essentially, the dots that one of the farms that Rumpus identified, which gave us the scale, which we all, when we applied it, we checked it, realised that it was probably right. I want you to show the lack of curvature, because although the Rumpus did correctly identify the farm or the light, which we agree with, there is no curve. So on the one hand, Nathan's been bumming what's his name, Rumpus recently, and every time he does it, I just think, no, don't, because I've been dying to say for weeks and weeks and weeks, yeah, Rumpus got the right identity of the land or the object, the subject matter that we were looking for, but there is no curve. So let's not overdo it. Let's bring Rumpus back down to a normal level. Yeah, he did identify the landmark that we wanted. That was what we needed to work out what we were looking at. However, there is no curve, because when you apply the curve calculator to the dots that Rumpus claims, those dots are sat on the horizon. And I'm going to drill this one home because this is where Rumpus can't get out of it. The dots that Rumpus has calculated for, he claims is consistent with the curvature of the Earth. Well, if that was really the case, although you may have got the scale, Rumpus, you haven't got the dots on the horizon, which is demanded by your model because of the thing called curvature. I can't repeat that anymore. I can't emphasize it any stronger. It isn't sat on the horizon, Rumpus. Why is that? It's because there is no curve. Why can we see Mackle Lighthouse? Whatever the elevation of my thing is, because, I mean, the simple fact is the elevation of the observer, nobody knows it at the minute. I'm trying to work on it because different models give different things, and it's not easy to work it out, and no ball earther or flat earther would ever chuck a tape down and do the do the trig and do the angles and all that. Nobody would do that. We would only ever go with the value that's on Google Earth because that's your working model. However, when you apply whatever's going on here, this lighthouse is gone behind the curve, and you need to be at. I mean, what's the actual elevation that I would need to be at, Chris, to be able to see that lighthouse? Mind you, we could just do that with the curve calcs. But point being,
on the ball, I don't know. You do it with curve calcs, yeah. I mean, you would have to be quite high. I think whatever it is to accomplish, you have to be at least higher than 170 feet of bulge, and high enough to see it at that distance. Like you'd have to be 600. I don't know. Don't quote me, but do the math. It's probably 400 feet in the air, isn't it?
Well, if I do 31 miles at 0 feet,
yeah.
The drop is 640 feet from the surface of the water. Now, there's a bulge of 161 feet, a drop of 640 feet. And then if you want to add the slightly looming non-standard refraction hyena calcs, that's the hologram figures underneath to bring things back into sight. Changes it slightly, but essentially the drop is 640 feet. So that's like 640 feet below your feet. At the point you're stood at the roadside or stood at the sand side, the beach side, it's 640 feet below your feet. To see that, to bring that back into sight, you have to pick yourself up to 640 feet to see it.
Is that
Is that
actually
right?
correct though? Because Soundly picked me up on that, and I mixed up drop figure with what I would consider to be hidden, i.e. behind the curve. And when I was in fairly casual conversation with Tim Osman, and I just basically didn't have the maths in front of me and misquoted which figure I was using, and I said 600 feet, and said you'd have to rise up 600 feet to do that. Now, at the time, I thought, do I need to correct that? So maybe, Chris, you can answer that question, or Anthony, you can answer that question, because I'd like to know, to my own satisfaction, how high you would actually have to be to bring Morgold Lighthouse and the amount of land that's beneath it back into perfect vision on a sphere. I'd like to know the answer to that, if you can work that out here and now.
Yeah, if you're on the site there, Anthony, go ahead, or I can try and go over there too while you're doing it, and we'll see if we come up with the same. Yeah,
well, at 31 miles, viewer height of 0, the drop is 640 feet below your feet because of the curvature of the Earth. That's the geometric curve of the Earth without any atmosphere. But if you want to add the slightly looming non-standard refraction hyena calcs, the drop drops from 640 down to 549. So it makes it 100 feet. Now, what that means is, just call it 600 feet for the average between the two. It's 600 feet below your feet. That's the base of the lighthouse. Is six or the coast on the other side of the thing where the beach would be if there was a beach. The bottom part where it meets the water would be 640 feet below your feet. So do you want to pull up the dodgy website with the diagram on it?
Well, if do you want to do that, Anthony, and we'll just swap who's screen sharing, and you, or I don't know, it's up to you, unless you've got it to hand, Chris. Do you want to change your screen, or if Anthony brings it up, one or the other?
Share screen.
Oh, have you stopped? Yeah, if you can bring it up, Chris.
No, I've done it now.
You've done it. Anthony's done it. Brilliant. We're on the case. Slick.
There we go. We'll get there. Yeah.
Right. So
I was trying to find the website and put in some numbers to see what'll happen here. So
Mackle Lighthouse, 31 miles on the beach, gives you a drop of 640 feet below your feet. That's where the other coastline is geometrically on a ball. Okay, nothing on that coastline can be seen less than it has to be 641 feet or more to be seen, because that's how much behind the curve of the Earth it actually is. That's the way I understand this, because it's got really confusing for me this recently, because I used to have this sussed, but I realised that it doesn't make any sense anymore, because this thing called bulge, and this diagram at the bottom now is confusing for me. I struggle with it now, because I used to think I had it, and now I realise that I don't have it, and it's not making any more sense to me anymore. It's changed the way I see it now, because it's just doing me head in. So
far that's right though. Like, so at 31.5 miles, right?
Well, before you do this, Chris, just so we've not got Anthony sharing his calculator, can you share your calculator as you do the numbers? Is that possible? Sorry to be a faff.
Let me see here.
You stop sharing, Anthony, and Chris starts.
I'll try it. Yeah. See if we're all on the. It should be this curve calculator, right? Make sure I'm on the right one. This is the popular one, right?
Yeah, looking good.
Okay, so 31.5 miles. And if you start with the viewer height of say 1, so it has something to actually calculate from.
Can you make it a bit bigger?
I don't think it'll work with 0 with it.
How'd you make it bigger, Anthony?
I guess it will.
Can you zoom in a bit, Chris?
Let's see, can I? And
How's
that? That's a little bit better.
Make it bigger, Anthony. There we go.
Maybe
Much
that's
better.
too big.
Thank you.
Yeah, there. Close enough. All right, so 31.5 miles viewer height. So this is basically 0, which would be the hidden is 600. The drop is 661 feet. The so-called refraction hidden is 567. So that's at 0. So the question is, how high would you have to be to see a lighthouse that's 200?
on the beach.
Well, yeah, but it would be, that would be it, right? right there.
It'd be 600 feet, wouldn't it? You'd have
You'd
to
have
go.
to be the exact opposite of that to see right down to zero again, right? You'd have to be 661 feet in the air to see back down to the beach level.
Right. So put the viewer height in at 661, and then the hidden value should become 0 or 1.
61.
There you go. The hidden becomes right. So basically, that drop value and the hidden value, you've got to get to that elevation to see it.
Yeah, no, that's exactly it. Yeah, you're right. 661. Because if you go below that, then it starts to hide stuff. So to see right down to the bottom of the lighthouse, you would have to be at 661 feet in the air to get.
Right,
So you're basically your horizon line. What happens is in this diagram as you go up, right? So you'd have to be high enough so that the horizon line meets the hidden object at its base, right? So you'd have to be that high in the air to see something that's on the surface down here. So you're right. 661 feet would see the bottom of a lighthouse at 31 miles.
So I did understand it. So when I
Yeah.
put that to Tim Osman in a very casual, I didn't even, when you're just talking off the top of your head, you're not putting any mental arithmetic together. You're just quoting it as you know it. So it just flows off nicely. I said you'd have to be about 600 feet to see it as you see it. And that is absolutely correct. So suck that soundly.
It would be, yeah.
Yeah, it's because what they do is they conflate. They don't want drop to be the reference. They want it to be this refracted hidden. That's what I mean, I was always taught refracted hidden. I say taught. There is no teaching. I was preached that it was the refracted hidden value. And I'd never even considered the drop value. But you're right, Nathan. The geometric shape of the Earth demands that the drop value is the geometric drop. That's how far behind the horizon it actually is.
Oh, absolutely, yeah. To have a straight line of sight and have that, to see the bottom of the lighthouse, you'd have to be at that elevation of 661 feet. Because as you drop, right, then the horizon comes back. So you're hiding more and more of whatever it is you're trying to look at because you're looking through this bulge of water, right? The lower you go, the less you can see. And the higher you go, the more you can see. I mean, that's pretty standard.
Can you clear something else up for me then? So when you're looking at the refracted hidden value, that would necessitate bendy light for anything below what you can't see. So I don't know if I'm terming that correctly. It's pretty late at night here. But basically, once you start looking at Mackled Lighthouse, it's below the bulge, 600 feet below your feet in terms of the bottom of the shoreline, and you're still seeing it in the picture. So they say, well, that's refracted. But when we sort of tied Paul Voigt and I think it might have been Rumpus on this point, they both basically said that the entire island was being refracted. Now, when you did your calculations on the top of Snaefell, that was absolutely the case in terms of the way they measured it. So correct me if I'm wrong, if you have things that are obscured that are in your camera, in your picture, therefore that necessitates on the sphere model the entire island being holographically projected, as I put it, to make a farce of it. But the entire island is looming at that point, correct?
Oh, absolutely, while maintaining perfect perspective and perfect squareness and perfect. Absolutely, it's a work of magic. Right, the entire island. Right, if you as an observer can't get high enough to see the bottom of this lighthouse and you're way down here on the ground, right? Then in reverse, this entire island is down here where it says hidden has to come up to your eye level magically to appear in a straight line of sight to you as an observer, right? The whole thing has to come up that 600 and whatever feet in reverse. It's a dichotomy, right? You can't have one without the other.
So am I correct in phrasing it? The entire island is being risen up 660 feet in this picture.
Absolutely. Yeah, absolutely.
So we've got a 660 foot high hologram.
Yeah.
Yeah.
It's nonsense. And the other thing is, when you were showing the you constructed something but using that curve calculator diagram, and basically the conclusion of the point that you were making was that when you look down, there's a bulge in the way, but because we're at the top of the bulge, it's hard for me to word this. If you can pull up that thing that you showed before with the model, where you put that 3-dimensional thing over the model. Not our model, but the refraction model.
The ball one or whatever.
Yeah. The ball one when you put that chunk over it, because you had some extra lines on it, and it was to do with. I need to see it to remember what it was.
Oh, I don't remember which one you're meaning now. I don't know. Yeah,
Oh,
I was playing with the light scatter through different gradients and refractive indexes of glass and stuff.
All right.
No.
Well,
He's talking about your the thing that you had at the beginning of this show. So it's just the ball with this cut through it with the meta bunk.
Yeah, that was the one.
Okay.
So,
okay, just a second. I do have that one. Yeah, if I just had it open here.
yeah, that's the one that I was referring to.
Switch screen window back to this.
Although that does remind me, Anthony, we must have a look at that because that's something that Chris was saying that he's just when he's been sort of playing with the model, if you for want of a better word. Some of those things just show us some of the cool stuff. You know, just have a goosey basically because it's cool.
Yeah.
Now, a lot of the ballers argue that the amount that you look down, you know, the angles of looking like perpendicular or horizontal. If you're looking truly horizontal, and the argument is that you look down, but it's such a small amount that you wouldn't perceive it. If want for a better word, negligible. Then if they're going to attribute the value of like a minuscule or negligible amount of angular drop compared to horizontal, then the same applies for this refraction nonsense. Now, if you do any of the basic maths on the refraction, even the standard refraction, it varies between 14 and 19% worth of refraction on the standard 7/6 of the radius Earth. It's 15% basically. 15% is not negligible. So either the angle that you're looking down from the horizon isn't the way you guys are telling us, or you're massively exaggerating the effects of this so-called standard refraction, because the effects of it should be negligible. That's what MIT say, and you guys are putting 15% to it and pushing it as true. I'd like to see an experiment that shows something from behind the curve of the Earth in the atmosphere ever coming back. So let's get a curve, basically prove that light bends the way you guys tell us it does over a flat surface and then over a curved surface and bring something back. Not using liquid nitrogen.
Well, you have to find an experiment that can show light bending through a curved medium while it maintains a constant curvature, right? So it has to. That's yeah, I'd like to see that too. Actually, yeah, that'd be really cool.
Even refraction soundly shows that light bends up as well as down, but all those curved maths always show that it's down. Never ever accounts for.
Well, yeah, I mean, I agree. Yeah, technically, what's happened, but if you believe it, if you believe that kind of standard or non-standard refraction hyena, whatever it is you guys say, if you believe that's happening, that means that the image of the lighthouse is traveling perfectly from here through a curved surface all the way up to you as an observer, so that you can picture it in your camera in a straight line of sight, right? Whilst also straightening itself back up to be perfectly perpendicular, right? But the light has to travel through this curved medium of air. And that means light is traveling a curved arc path, right? And I've never seen anything where light can travel in a curved path.
Well, they say that
even when Snell's law, like if you look at that, even Snell's law, when light hits a curved refractive, like a curved surface, it'll hit the lens, which is curved, and then it hits the lens which is curved surface, and then just angles through it in a straight line, right? Light is straight, right?
Well, that's what I was trying to drive at with him doing a per pixel calculation from left to right. He's drawing a straight line.
Mm-hmm.
So if the curvature applies,
here's a good way to demonstrate that. I can kind of demo that here too. Like what you're saying is, all right. So this is our object over here that I have highlighted, which is on the curved surface, angled backwards. And our camera is at the top of the ball, and this is the diagram from that site actually that we were just looking at and playing with. So you put it to the test. So you say, okay, I'm going to take the camera and I'm going to angle it down, like they say to do. Angle it down. See camera. Cursor to selected. Angle it down. Let's see, until I'm looking at the bottom of that object. Right there. Okay. So now the line of sight of the camera, let me take it up just a little bit, trying to be as accurate as we can. Rotation. Camera right there. Okay, so the line of sight in the center of the camera is looking at the bottom, and we'll call this our lighthouse. So this is our lighthouse. Line of sight is intersecting way in here. That little blue line where it hits this object is center of the camera, looking down. Left-hand side is, here's the object. This is the bulge you're looking through, but the camera's trying to look at the bottom of this object here. So all we need to do to test the theory is to grab the camera, in theory, and bring it up until we see the bottom of the lighthouse or the object in question. Right there. Should be quite high, actually. This is kind of simulating what that, in theory, should be doing. Right? You can see that you'd have to be equal to the height. Turn this off here. Right. So to see the bottom of this object in the camera has to be that high. And looking down, now that we've risen in our altitude, we can now see that we have a clear line of sight without being obstructed by the bulge to the bottom of this object over here. Right? There's no getting away from that.
So basically, like the lighthouse sits at 80 feet or whatever it is. It gives a total focal height of around about 200 feet from memory. If the drop value is 600 feet and the lighthouse sits at 200 feet, that means you need to be at 400 feet to see the tippy top of the lighthouse. Right?
Yeah, pretty much, I guess. Yeah, you're right. Yeah, sounds about right. You know, we're talking easy figures. Yeah. Right. If all you could see was the very top of this lighthouse, if this is our lighthouse in this example, and grab the camera and go down, and we're going to say that somehow you're obstructing your view, then you got to bring the camera back up until you can just barely see the top of the lighthouse. Right, it would be that kind of idea in reverse.
So I don't
see it, right?
I don't know how we'd have won this debate if it wasn't for Gemma identifying that lighthouse.
The other thing that's quite nicely shows...
This obviously isn't the lighthouse that we're talking about. It's not the scale, but it's just trying to give you the idea that...
Yeah.
Right. You would have to... Yeah, it makes no sense.
The thing I'm hoping
if you're going to see something, in a straight line of sight, well, then you need a straight line of sight to it. It's simple as that. Right?
Yeah. Otherwise, you believe in holograms, fantasists.
As soon as that refraction figure starts being used, essentially you're into everything being a hologram, and that's something that I've been, being ridiculed for asserting, because it's your belief, Globers, and this is something that the ridicule's been levelled at my door for pointing this out to you. Your nonsense that you must believe. You ridicule me for pointing it out to you. I don't believe in holograms. I believe in straight lines of sight and just seeing stuff. But I'm a flat earther, and that's perfectly fine for me to accept that I just see stuff with a straight line of sight. Like Rumpus calculates his left to right measurements with straight lines and angles. That's normal. That's reality. However, the rest of the globe fantasy necessitates that the entire island's a bloody hologram. That's what you've got to believe. And for the flat earth side of this argument, start pointing this out to them, that they're hologram-believing fantasists. Shout out to slightly looming non-standard refraction hyena.
And the other thing is, you've been ridiculed for the hologram fantasist side to it. I've been not ridiculed, but attacked, and you name all the nasty stuff, whatever nasty adjectives that you want to use, for citing the elevation given on Google Earth. Yet this is your model, guys. Right? Let's remember this. There is geometric curve in the way that stops us from seeing stuff. That drop value it's a geometric drop. It's not a fantasy. It's a fact. And when Nathan's been talking about it, and you guys have been like basically like trivializing it, you're trivializing it because it goes totally and utterly against the idea that we can see stuff. We see stuff because it's there. It ain't no hologram. We don't live in a holographic universe.
Like, that's it. I agree. No matter what you do, you can't get away from the physicalness of a ball, right? And I'll take it. You can take it from whether it's the curve ball of a globe model, or the sun, or anything else, and put it into these models that you're being told and sold, and test it. Right? I mean,
sorry, Chris. Let me just interrupt. Let me interrupt a sec. I don't mean to interrupt, but I want to catch this comment before it disappears. Imric says, Nathan, you can address this. It says, Sleeping Warrior, the answer is 150 feet high observer height would show the entire lighthouse without refraction if the tide was out. How do you want to respond to that? 150 feet, given that the drop is 600 feet.
Would get you to 20 feet shy of the bulge, so you still wouldn't see any of it. That's the first point. And if you got up to 171 feet, assuming that it's a 170-foot bulge, you'd start to see things. Start to. But he's not at 170 feet. So the bottom line is, before he gets to 170 feet in elevation, all bets are off for the globe. All of this stuff is holograms. All of it needs slightly looming non-standard refraction to come to the rescue. Because he's not at 170 feet. So the bulge is in the way. That's the bottom line here.
So
the wall
that
everyone takes the piss out of when I say there's a wall in the way. There's a wall in the way. You're on the other side of a hill, and the globers don't get it, the thick ones, which is frustrating as all hell. Because you're like, what are you talking about? There's a bloody wall in the way. Oh, what do you mean a wall? Yeah, you know what a wall is? Suddenly they can't conceptualize a wall. It's literally that dumb that some of the people we're dealing with. They're either completely stupid or their cognitive dissonance is so severe that when I say, you understand that there's a wall in the way, you can't see through it, and they go, what do you mean a wall?
Yeah. It comes down to the bandwagon fallacy application, because if they all think that they're all together and everybody believes it, it's therefore true. They all fall for it. And I did a lovely little video this afternoon.
I agree. You're exactly right.
So
if they all believe it's true, it's true.
Curve Water says a hill is a rise in elevation. Well, that's where you've got a contradiction in terms of metabunk. Maybe you should go and have a word with Mick West, because according to gravity, you're at the top of the ball, but according to his calculations, you're looking through a bulge, which necessitates the bulge being higher than you are, Curve Water. Go and have a word with Mick West. Point out gravity exists in your world of bullshit.
I don't think any of these balls. I mean, look at Paul Voigt. Simple geometry shows that 150 feet of elevation would allow the entire lighthouse to be seen. Don't you comprehend this? You're an imbecile at basic geometry. No, Paul. Something that's dropped by 600 feet cannot be brought back by putting your elevation up to 150 feet. Don't you understand what a drop value is, Paul? Is it beyond you? Of course it's beyond you, Paul. You're a high school teacher at best.
I don't think he's a physicist. I think he's a bin man, based on some of the comments.
I don't think he's a physicist.
You know, he doesn't have any... He has a very rudimentary understanding of these things that we've literally just explained to him.
Higher is further from the centre. Well done, Curved. I love the troll account Mick Pest.
So we've hijacked you, Chris. Sorry. The trolls have taken over for a few moments. Reality will now become normalised again, and we'll talk about what you're actually showing, which is far more interesting than the idiots that we have watching this show who used to join.
So, just for the benefit of Imric,
hold on. I've just given the floor to Chris, and you've just nicked it off him immediately.
Oh, sorry, I was yawning. I couldn't hear half of what you said.
I said, "What are you showing us?" I was doing a little ham-handed segue to get back onto what Chris is doing.
Sorry, I was yawning.
Well, I was trying to get back to the point where you that you can't, no matter what you do, you can't get rid of the geometry and the physicality of a physical object being obstructing your line of sight, whether it's the bulge of a ball or a mountain or a wall, right? If you have something physical between you and whatever it is you're looking at, unless you have X-ray eyes, you can't see through it, right? So once you get your head around the problems that presents, not just for the globe model, but anything that's physical,
Yeah.
right?
So
And
I
apply
agree.
that to. I'm going to take it right here and go back out to like, for example, we're trying to target Saturn, and you're on Earth in the heliocentric model done to scale, where you're on Earth down here on this little ball. There's the moon. Right? The moon's there. Earth camera. You're on a camera, looking through a telescope from Earth, trying to target Saturn, which is in an orbital path around the sun, and you're going to try to look at the sun. And this is actually an animation, so you can scroll through it and say, okay, here's the Earth going around, and Saturn is traversing, and that's Jupiter to the right. Right. Well, the problem then happens is when you have the Earth on this side of the sun, and you're trying to look through the sun, which you probably can't do, and Saturn is behind the sun in a very slow orbit of 30 years, meaning, it's going to be behind the sun for a long time in its orbit. You're the only one that's supposedly moving in this so-called heliocentric world, which I don't think exists. It means that on this red line at 90 degrees, you're looking through daylight skies, right? So this would be daylight, right? Because you're still on this side of the sun. So on the ball that you're standing on, you have no choice but for this side of the sun. Everything on this side is daytime to you. Everything on this side of the sun, on the back side, is in shadow. So this is nighttime to you. Anything, this side of the red line up here is daytime. Anything back here is nighttime. So hopefully that's clear, right? Which means daytime exists for you until you get all the way around here. Right. So the only way you can actually physically see Saturn, right, is if you're in the night skies. So the only way you'll see Saturn is if you're actually around the back side of the sun on the same side of darkness, right, with your camera. Right. Sun's over here. Daylight is this side. You're now on the dark side of the Earth looking back at Saturn in the night sky. Well, that makes sense, right? But when you're on this side of the sun, there is no Saturn, because now you're trying to look through a daylight sky through the sun to see Saturn for 6 months of the year.
So, based on the heliocentric model, we should only see Saturn 6 months of the year, and we see it all year round.
Well, you'd have to try to figure out the angles and calculations, but for sure, you wouldn't see it, right, as long as you're in daytime relative to its position in orbit, right, because it is a moving object. So it would probably change, but technically speaking, in rough numbers, yeah, through this 90-degree arc, when you're in daytime, you shouldn't see it at all. But yet, if you go to date and time or any of these calculations, Saturn and Mars and whatnot, find me a site when it says that they're not visible year round, right? They never go anywhere. Their dimness changes and so forth, like their magnitude of luminosity changes up and down. But I was looking at one the other day and trying to find a year when Saturn is not visible, like for a period of time, equal to, months at a time, 3, 6, 4 months, whatever. Yeah.
Absolutely awesome.
Makes no sense to me. Because in the top part here, you can see that. Maybe if I zoom out here, can I do it that way? Turn off the atmosphere and go into a material view here. Might be a little more comprehensive. Turn on the stars. Why not? All right. And let's turn the camera if I can. Because this is kind of fun to play with this kind of stuff, is to prove the heliocentric thing to make sure it works in all aspects. So, let's see, camera. Maybe I can turn it on the other axis here. Let's make Y up. it makes a little more sense to our brains if we put the camera looking sideways. So basically, what you'd have to be doing in this sense is be standing on the earth, looking sideways, like laying on your side. But anyway, it'll be easier to understand, I think. And you roll through the animation. So now you have Saturn. Let's go back to this way. So, all right. So you're on Earth. You're rolling with the ball. Now you're coming. Saturn goes behind the Earth. Right. So you have to contend with one. You have to contend with the fact that you're on the backside of the Earth trying to find Saturn. Right. So this black spot is basically the Earth in your way. Right. And it would not reappear again until you come around the other side. Right.
Right.
Because right, you know what I mean? Like you're physically on the backside of the Earth on the night side trying to look at Saturn and Jupiter. They just disappeared over the horizon because they're on the wrong side. Right? They're on the daylight side of the sun. This is Saturn, this is Jupiter, and you're here on the bottom part. Right? Which means you're on the backside. You're on the dark side trying to look through the Earth. You physically have to look through the Earth to see them. That's another problem.
This is where flat Earth wins. We're never on the backside of the Earth on a flat plane. So these problems don't exist.
No. Right? Because I started asking questions like, if I put the atmosphere back on here. Atmospherics. And now hopefully we zoom in on the bottom. Will this work? Let's see, top view. Yeah. My main question was, why is it that all these animations and stuff you'll see from science sites and NASA and everything else, why is it that you'll very rarely see an atmosphere? You'll see some balls spinning around showing you this heliocentric model and whatnot, right? Why don't they ever turn the light on, like the sun, and then show you where the shadows are, right? Like where's night and day?
That's what he said on Patricia's show. You know, when you were saying it, I was thinking, what's he leading up to? You know, you were saying about the dots that they put in, and you can see all of the different movements, and then you turn your light on. I was like, oh yeah, you're going to get all sorts of different eclipses and shadows that, you know, they're never shown to us. We just see Saturn as it is, with its quoted weather traversing its surface. Well, what about the shadows? Where are they?
Yeah, so the fan's going to kick in here and make my voice sound weird, but I'd like to show this point to people. So if anybody's watching, right? So no matter what phase the sun or the moon is in, the Earth must also be in exactly the same phase. Right? If the sun's over here shining this way, it means that half the ball is basically lit up, and you get some scattering through the atmosphere. A little bit more than half, so you'd have to turn the light on. And if you're standing in the dark side, or if you're standing in the light side, you can't see anything for stars because it's daytime. Right? You can only see the night sky on the dark side. And then if I turn off the atmosphere and stop rendering here, because it really makes the camera go crazy. Let's go back into the wireframe, for example. So now you can physically see that you're trying to physically look through the Earth to see Saturn and Jupiter, and you're on the back side, in the bottom here where I just showed you. It's still nighttime to you because you're in the shadow, but you still can't see those objects because they haven't risen to you yet, because you're not around the other side. Right? Because the sun is over here. This is the sun, that's the Earth. You're trying to look at Saturn. That's a problem, right?
Sure is.
Because if you come back around this side, right? Because Saturn is such a slow orbit. Right now, everything you see is daytime, and Saturn in a three-dimensional sense, is on the other side of the sun for years. 15 years or 16 years it'll spend on this backside. I think it's around a 30-year orbit, right? So it's always 15 years one side, 15 years the other, right? So, which is very strange. Like, if you think about it in terms of light, right? Half the globe would see the Saturn for 15 years, and the other half would see it for another 15 years. But depending on if it's day or night, only half the population would ever see it. That type of idea, right? If you really wrap your head around that, right? There should be Saturn festivals when Saturn's actually visible. Whatever, Jupiter Fest, right? When they come back to life, when they rise from the dead. Yeah.
We're going to get
Doesn't
into
happen.
some heavy philosophy.
Yeah, that's getting pretty heavy, but you kind of get the idea, right? Yeah.
And for the benefit of anybody, we had a chat this morning about parallax. And basically, there is no parallax. They say that there's microscopically small amounts, like fractions of a degree. If anybody can model it on CAD for why there is no parallax, I'd be really interested to see it. So the likes of Sly, Rumpus, people like that can use CAD, show us why there is no parallax in the night sky, because there definitely should be parallax. All the stars should be parallaxing each other in all directions, all of the time, because there is three moments of movement. There's the orbit of the sun, there's the axial rotation of the Earth, and there's a movement of the sun going through our cosmos. And all them stars should be parallaxing each other, and we don't see it. Anybody got any reasons for why?
Yeah, technically, like if you maintain your focus on the moon, for example, because the moon has a slower orbit than the Earth, supposedly the Earth spin, right? So the moon for one night would stay relatively stationary for that night because it takes 30 days to go around, right? So if you started on, say, the west coast and you're rotating backwards to the east, and you have your camera focused on the moon, as you get to 90 degrees and you're looking dead center, so the moon's at high noon, right? To you as an observer, as you cross that median point, you would see essentially the moon would appear to actually stop, go backwards, and start again, because there'd be parallax against the stars. Right? If you maintain your focus on the moon and go around in a circle, you should see that parallax every night.
The moon. Sorry.
Or any of these objects, right?
How does this work then, right? The rotation of the Earth is different to the orbit of the Earth by the moon. Okay? It takes 27 days for the moon to orbit the Earth, but the Earth spins on its axis once every 24 hours on the heliocentric model. That means that in the night sky, the moon should be moving at a different rate to the stars, because the moon and the stars are not. The moon is not geostationary to Earth. It's spinning at a slower rate on the heliocentric model. So the moon and the stars are all, when you do a time lapse or a long exposure, no time lapse. And Red's Rhetoric did one. You can look up at the sky and you can see the moon and the stars are always relative to each other fixed. That is impossible if the rotation of the Earth and the orbit of the moon are different, and they obviously are different. And the stars cannot be fixed with the moon. Simply impossible. I'd like to see an explanation for that one as well. A working explanation. For those of you that don't understand, who was it that was asking about orbital mechanics? Jazzconda, wasn't it? There's another one for you, Jazzconda. If the Earth spins once every 24 hours, but the moon orbits the Earth once every 27 days, the moon cannot be fixed in the night sky with all the other stars. It has to move. Doesn't do it. There's another debunk for you.
Did you want to give any Isle of Man updates in terms of what's going on this weekend? Let people know what.
Yeah, there is. There's still no curve this weekend, last weekend, or next weekend.
Yeah, that goes without saying. I mean, I put a link in the chat just now for Twitwit specifically because she said, I typed in the Earth is obviously observably flat, and she said, let me know when you got proof of that. Well, literally today, we've presented a model, Twit, that demonstrates how reality actually works, and it was modelled on a flat plane. I'll remind you that the globe equivalent fails completely to model reality. Just to point out once more, just for Twitwit, that modelling reality is easy to do if you use a flat plane and impossible to do if you think you live on a sphere. Just for Twitwit.
Twitwit sounds like Thelma off Simpsons. He's got a deeper voice than me.
So yeah,
Okay.
Did you want to update about what we're going to do this weekend, or is it we're not going to let any of it out until we actually do stuff?
I don't mind. It's up to you if you want to share.
Share.
I think
tell them what we're doing.
The only one that's worried about it is Spurs Chemo.
Why? What's he worried about?
Don't know. He just doesn't want everybody knowing because I think he's paranoid that he might get his head kicked in or whatever. I'm not sure. He's just. I don't know. Should we say something or should we say nothing?
I don't know. Okay, well.
Did anybody happen to see like New Zealand and the Philippines and China, Eastern China, or basically Southern China, etc., in the Tesla footage there from the guy from the Tesla car?
Australia only, you said. I saw.
I was wondering. Meme. I was looking.
You made a meme of this, didn't you, Chris? I'm sure it was you.
Yeah. I was trying to see if anyone else had come across any footage that showed the Philippines, China, New Zealand, or anything else other than Australia that was visible in that footage, like at any point in time.
Have you got that meme to hand? Let me know when you have, and I'll put you back up. But
yeah, I don't have it here.
No, don't worry.
Maybe it's just on. Yeah,
interesting one. We've been doing this for a few hours now, guys. So I don't know about you. I'm pretty knackered.
I'm good to go. I'm good to go. Yes, probably. I think we've probably chatted enough about that stuff. Yeah.
Cool. Anthony, this is normally where you
on to flatter better things. Yeah. Hey.
Yeah.
Anthony, did you want to what?
Well, this is normally where you'd say "F you Globers" and things like that sort of nature. I just want you to get it all out before I round out. That's all.
Miles Davis tells lies. Paul Voigt swears far too much, given that he's supposed to be some kind of professional. Cat Earth thinks there's a beach everywhere. What else is it that we need to say in here? Twitwit does sound like Thelma off Simpsons. I can't see anybody. That's about it, really. I don't know. I really want to tell them about this weekend. Should we? Maybe.
Just do it. Just do it. Who cares? I don't care.
Well, all right. So here we go. We'll be doing a broadcast. Hopefully, we'll be doing a broadcast from St. Bees later on this weekend.
Oh, you bastard! So somebody could have said, well, depends how much fun we're having and if we have a few beers, and I don't want to do a broadcast unless we're bored. And you've immediately tied me to doing one, you sod.
I thought that's what you were referring to.
Not at all. I was just, I was just going to say we're going to be doing things like measuring to actual sea levels and things of that sort of nature. But clearly the actual flat earth sciencey bit is not what you want to talk about.
I thought that was already public. Most people knew about that. Yeah, all right. So we're going up this weekend, and we're not going to be doing a live broadcast. Possibly not.
Might do.
And really, all we're going to measure is how tall is that highest cliff, the tallest one. We're going to measure how tall is the lower one at 35, and we're going to try and get a couple of pictures at high tide and show Miles the Liar Davis, where high tide really comes to, from a perspective where we can see it. Because Nathan said the guy at the bottom, which we think was Al Kay with the rod, would have been getting his feet wet if it was high tide. And I agree with him. He probably would have been getting his feet wet. Maybe not, but that's where we think it is, given that it was the highest tide and it was the high tide of the highest tide of the week. Like, that's the authority for saying that. And we're going to try and get the high tide picture to show exactly where it goes. So we're going to be doing quite a lot of measurements. We're not really going to be doing any observations. But hopefully, if the weather's reasonable, we'll be able to do this, and we'll come back with some figures and facts and evidences. And by the way, there was one thing. I've got a spirit level with me, because Rumpus has basically He's dismissed my calculated or measured angle from the vertical because it didn't conform with the sphericity of the Earth. So what he's done is he's conjectured with a totally made up horizon value and shoved in a 30-degree thing, a 30-degree angle, because that does support the sphericity of the Earth. And he's challenged me, or not challenged me, but he's criticised me for not using the spirit level to go measure the angle. Well, Rumpus, all I've got to do is show what the angle of that hill is, and the hypotenuse isn't going to change.
Jump in here because
so we'll be doing.
I'm going to speak over you. I'm really sorry, but I've already said Arwen. Shout out to Arwen. He's in the chat right now. But Arwen brought this up, which is that you're pushing a ball up a hill, right? And Chris and I have both got exactly the same attitude. Hopefully he'll back me up in a moment. We'll see just before I round out. He might go silent. We shall see. But yeah, this hill that you're talking about right now, which, as you correctly point out, you've now got various extrapolations, something that I was always very concerned about. And this is one of the reasons I discouraged you from releasing this information, especially about the hill that's now in question, which is that you can easily argue about the angle, which is precisely what has happened. No shock. However, this hill is of virtually no importance to me. The amount of time I'm prepared to dedicate to it personally will be taking a photograph of where the high tide reaches, and then that'll be it. It'll be moving on to the high observation point as probably the highest priority, because that's where the composite's made from, and that's where the model's made from. And we've also got, I hope we get in touch with him, he's been busy working, but the guy on the Isle of Man, Besser, so hopefully we can get hold of him, because we want to take some real world measurements, i.e. so we can cut loose of all of these various different datums, these various maps, these various models, these various CGI renderings, in terms of what they tell us the height above the actual water is. Now, it may be initially that we have to take some further extrapolations once we've got the height above high tide, which is what most practically we can measure to, but it's getting better all the time. And formally, my thoughts were to get a really good idea of the height of the hill, and then start measuring down the beach to get an idea of tides. But I think that's probably going to be a next thing. That'll probably happen next time. But I think a better thing to do initially is just to get literally the tape measure wet. Get it to the water, so we can say this is an exact measure above water in terms of elevation. And that, for me, is really only applicable to what Google quotes at 34 and 52 off the top of my head. But those 2 points, regardless of what they come out to at this point, the debate for me in that respect is kind of over. For anybody that says, the Isle of Man is X, Y, or Z in the negative, or hooray for Isle of Man, it's like, no, it's now been presented as is. Go and check it out. The video, Flat Earth Debate. I think it's not even Flat Earth Debate labelled. I think it's called Flat Earth QED model or something like that. QED Flat Earth model Isle of Man. So that particular video, go and check it out. That is a fairly raw example of what the Isle of Man has actually built up to, i.e. a working model of a flat Earth. And that's exactly what's been presented in that respect. So go and check out that video if you're ever told that there is no proof of a flat Earth. But in terms of how accurate that model is, yeah, some of the elevation figures have been taken as averages and quoted figures. We can't deny that. So to get the model even more accurate in terms of how well it will represent heights and values to the to even more detail, the way to do that is to get accurate measurements of the hill. In that respect, I don't care what the figure turns out to be. So before the show, Anthony and I were chatting, and they're like, well, if it comes out like this, it'll be favourable. If it comes out like that, it won't be favourable. It's like, no, we're beyond that now. It doesn't matter what the hill measures, because all we need now is accuracy. So hence, when Miles Davis measured the higher observation point, that's useful. We can take this information. And just to round out, earlier on in this show, you were saying about, pointing out the sort of lies and stuff that people have told along this journey. And for me, I still want to commend people like the Rumpus. And again, I hope Chris backs me up on this point, because these people are working extremely hard, and it demonstrates to the audience how seriously these people take this stuff. For someone like Miles to go down to St. Bees and to risk life and limb climbing up a 45-degree angle, I'm going to go out on a limb and say thank you, Miles. You know, it doesn't matter how he presents his conclusions. We can debate about those, and that's what gives me a show. So again, I can only thank Miles as much as it frustrates you for me to do so. And, you know, over to you, Chris. I'm hoping you'll sort of echo my sentiments in terms of the work that Rumpus has done.
Yeah, no, I agree. It's Rumpus has actually done a lot of, excellent work as far as the mathematics and trying to figure stuff out, and his honesty, and I respect that. He's put a lot of effort into it, so it's a very serious deal, right? So 100% agree. Just keep pushing that ball up the hill and try to look over the curve.
I'm gonna disagree.
It's a flat plane, right? So
I'm gonna disagree. The Rumpus made some relatively good points, but he is getting way too much credit from you, Nath. I don't think you should give him as much credit because he has literally manipulated the mathematics on that last measured angle to benefit Miles with a totally guessed nonsense horizon. And he rejected the vertical that was in the picture. He used a different frame of reference than what I did, dismissed the one that I used that was vertical for no good reason, and basically fudged the figures and rounded things up to try and help Miles. That's called dishonest, in my opinion. So
that's what I'm hoping to demonstrate. Again, I would thank him for that. I know it annoys you because you're, I know I'm not neutral, but by the same token, I want to at least appear to be neutral in the respect that if you don't have that information presented, you can't demonstrate to an audience how slippery you've got to be to manipulate these figures in order to make it appear like you're on a sphere. You know, in that respect, when you're talking about him manipulating the angle, well, what you're trying to get to is him trying to get that much closer, foot by foot, to what ordnance. It's like, who cares? Literally, that's why I said what I said a moment ago. At this point, I don't care about what Ordnance Survey or Google say. All I'm interested in is reality and getting the model that we just presented to be even sharper, to be an even more slick tool. At the moment, it's very, very, very good. Well, it's not perfect. It'll be perfect when we've got accurate measurements of what those hills actually measure. And going forward, it may be that the model changes subtly in terms of the observations that come forward from this point on. So you said, we're not going to be taking any observations for various different reasons this weekend, but you will take more observations. You will do them at various elevations, and it may be the case that you get it to a more globe destroying position because you get the lighthouse from the lower observation in a full composite, for example. Well, those things may indeed come, but for the time being, what we have is a genuine representation of reality that's been put under the microscope and sliced up with a very sharp scalpel through some very sharp minds, and they are fighting, and I mean fighting, as hard as they can to prove sphericity, and there is none. And, I'll say it once more, shout out to Twitwit, go and check out QED Flat Earth Model Isle of Man, or Isle or Man, as I've misspelled it on the re-up. I'll change that as soon as this broadcast is finished. But yeah, check out that video, and it is a very simple demonstration with simple angular measurements, simple straight lines. There's nothing complex, there's no tangents, there's no arc calculations. It's raw as it comes, here's reality, and it's simple. That's what you want when you're presenting something to an audience and trying to present them that is your reality. It's simple. This is it. This is how the world works. You do see in straight lines, and when you take that into consideration, you can measure things if you model it on a flat plane. If you don't model it on a flat plane, you have to have a team of 10 people, go through 3 fairly humble guys. Ranty, unfortunately, is absent now, but he does deserve a lot of credit, and I will do him before we round out. But it took a whole team of people crunching the numbers to do something that Chris has demonstrated in a few seconds on a model based on a flat plane. When you're trying to do it on a sphere, you've got to be very tricky. You've got to work as a team. You've got to obfuscate the point while you try and get a calculation together. And ultimately speaking, it still falls short and doesn't represent reality. It still can be picked apart in the respect that you're only applying these formulas on the vertical and not on the horizontal, which is fallacious. It's untrue. It's not reality. And that's, it's taken a lot of strife from a lot of globe heads coming your way for us to be able to put that long, very long sentence together. And that is to say that there's people out there, it demonstrates they're willing to fight for the consensus reality that people accept. Why? Their motivation, I don't know. In some respects, like this morning, we say, it's because they already know the Earth is flat. But we don't know that for certain either. But ultimately speaking, it demonstrates that quite nicely, that these people have gone to these efforts, that it's been 60, 70, 80 debates on this one observation, this one string of images, this one little video. It's amazing to me. I think it's absolutely glorious. The end result, I'm elated with. I'm so chuffed with the presentation Chris did earlier. I'm made up. This for me is my prize. So, there will be more observations from the Isle of Man. It has definitely got more meat on the bone. But yeah, I'm made up. I'm really pleased. And I just don't want you to feel like the guys like Rumpus deserve constant berating for pushing their side of the debate. They're going to push it hard. They have, and it demonstrates how strong their motivation is. And it gives us a lot to criticise. That's the show. That's Flat Earth Debate. That's what this particular special edition is. It's a Flat Earth Debate special edition. And without those guys, we'd have nothing. We'd be a total circle jerk.
Just two last things, and then I'm done. Somebody in chat's asking why can we address why M. Scott Veitch was no show on Patricia's show. As far as I know, he agreed to do Patricia's show, and then he cancelled with her the following day, basically because he felt that Nathan was a bit unfairly harsh with him, and on that basis, he didn't want to do it, which I think is a wimp cop out. But as far as I know, he cancelled on her. So he didn't no show. He did cancel on her, but he basically hasn't really got a good enough reason not to. But I think it's because he's in the public eye, and I think he thinks it would be bad for him. And the second one was, can't remember the second one.
For a minute?
So I
don't mind.
Yeah, that's done. I'm done. I've forgotten the second one.
Okay. Anything you want to add, Chris? It's been a bit of an epic evening.
I think I'm pretty good. I think I've kind of said what I needed to be said. I don't know. I've just been playing in the background here, looking for the so-called.
Oh yeah, that's what I was going to say.
Retrograde motion and whatnot, and testing to see. I'm actually just testing this so-called solar system model to see if it actually holds any more water than the globe.
I've remembered what I was going to say now.
Because, you never know. You might learn something out of this. If you actually investigate this, you might learn something that you could apply to the reality of the flat plane model. Right? So, research both sides. Give them an objective opinion and honest shot. And if it fails, just be honest about it. So what? It failed. Move on.
Yeah. Cool.
I remember I've got my second point.
Go on.
There was a
Have a good night, everybody.
Thanks, Chris.
There was a comment in chat that says, Nathan is so chuffed. Every single claim they made about this has been refuted. Well, the 4 dots that are on the far left-hand side that Rumpus has identified should appear on the horizon. They don't appear on the horizon. There's about 300 feet of elevation between the dots and where they should be on the curved Earth. There is no curve to the Earth. The Earth is flat. The evidence doesn't match the curve of the Earth. So even if you think that you got some kind of refutation over the observations that were done, there's still no curve there. So if you think you can show where the curve is, be my guest.
Check it out. So I'll start streaming again. So I'm back online just in case. So apparently none of that outro got to the audience, according to Anthony. So I will repeat it all because he said it just went silent. Me being tired. It is, to be fair. What is it? 25 to 1 in the morning. So I'm going to do another outro. It'll only make it to the live audience who are still watching this, going, "What the hell is going on?" But nevertheless, massive thank you to all of the live audience for tuning in and hopefully sharing this debate. Not that it was a debate, more of a chat with the comment section, but thank you very much. Be sure to tune into the re-up on Nathan Oakley 1980 channel. And yeah, that's pretty much it. Thank you very much for watching. Thank you to Anthony Riley and thank you to Chris Seeley. I've been Nathan Oakley and I will see you all in the next video.